In the last video, we introduced the rotational equivalents of the kinematics quantities, angular displacement, angular velocity, and angular acceleration. In this video, we will explore the rotational equivalent of mass. You're probably wondering why we even need a rotational equivalent of mass. The answer comes from looking back at Newton's second law. Newton's second says the overall force on an object is related to the acceleration that the object exhibits. The greater the mass, the harder it is to achieve a desired acceleration. So mass is a proportionality factor that tells you how hard it is for an object to undergo linear acceleration. Now what we need is a corresponding proportionality factor for rotation, something that tells you how hard it is for an object to undergo angular acceleration. Mass is not sufficient for this. Consider this skater. Her angular acceleration clearly increases when she draws her arms in, but her mass is unchanged. For rotation, we have to account for both mass and shape when discussing resistance to angular acceleration. And that isn't even all, because the difficulty of rotating an object also depends on the location around which it is rotating. A wheel rotating about its center will be easier to spin than a wheel rotated eccentrically at a point not at its center. Fortunately, we have a quantity that encompasses all these factors. It's called moment of inertia. It is symbolized by the letter capital I, and it has units of kilograms meters squared. Moment of inertia always has to be calculated with respect to the center of rotation, which may or may not be the center of mass. If an object is free and unconstrained in its motion, it will always rotate around its center of mass. So this is another reason why the center of mass is important. It's possible to rotate around another point besides the center of mass, but an object has to be hinged there for such rotation to take place. In this video, we will just demonstrate how to calculate the moment of inertia. We'll talk more about what it means and how to use it in future videos. Here, we see two small asteroids orbiting each other. One has a mass of 5 kilograms and the other a mass of 1 kilogram. They are 10 meters apart. We see them orbiting their common center of mass, which is what you expect since neither one is hinged anywhere. To find the moment of inertia in this case, we first need to solve for the center of mass. We saw how to do this a few videos ago. Draw the particles on a Cartesian plane, take the mass of each particle, multiply by its x-coordinate, add up the products, and divide by the total mass. We find the center of mass as being 1.67 I hat meters. Now for the moment of inertia. Remember that the moment of inertia has to account for both the mass and the shape or locations of objects. For a set of particles, we calculate the moment of inertia like this. Draw the system again, this time placing the center of rotation at the origin. In this case, the center of rotation is the center of mass. Then apply this equation. The letter r represents the distance from each asteroid to the center of rotation. So for each asteroid, take its mass and multiply it by the distance to the center of rotation squared. Then add the contribution from each asteroid. The moment of inertia is 83.33 kilogram meters squared. This is a relative measure of how hard it is for the system to rotate. Now, what if we had to calculate the moment of inertia for a continuous shape like this rod around its center of mass? The rod is 3 meters long. Its cross-section area is 0.2 meters squared, and it has a uniform density of 15 kilograms per meter cubed. The basic process is the same, we first find the center of mass before calculating the moment of inertia. The only difference is both calculations are now integrals. Let's work out the center of mass first. We can substitute all known values into the formula. The limits of integration are the endpoints of the rod, 0 meters and 3 meters. We simplify the two integrals, take the antiderivatives, and solve at the upper and lower bounds. Then we subtract and divide. We get a center of mass at 1.5 meters. Before we go any further, I just want to point out that the denominator of this fraction gives you the mass of the rod. To solve for the moment of inertia for a continuous object, we need to solve this formula. The book explains it slightly differently, but this way is a little bit simpler. As in any integral, we need to take a continuous object and slice it into thin slices. In this case, each slice has the same cross-section area, 0.2 meters squared, and the same density, 15 kilograms per meter cubed, and the same thickness, dx. They only differ in their positions, their x-coordinates. You will notice that, as before, I changed the location of the origin to match the center of rotation. We always have to do this. The variable r represents the distance from the center of rotation to the slice. But the center of rotation is the center of mass, and we moved the origin to align with both. So the distance from any slice to the center of rotation becomes the location of the slice, its x-coordinate, minus the location of the center of rotation, which is 0. So basically, we replace r with x. We now substitute all we know, the density and the area. Then we simplify this integral. The limits of integration are the locations of the endpoints of the rod, negative 1.5 meters and 1.5 meters. Now we perform the integral and substitute the bounds and subtract. We get a moment of inertia of 6.75 kilogram meters squared. Again, for this video, we'll just show the calculation. The importance of moment of inertia will be shown in later videos. Now, what if the object isn't rotating around its center of mass? In this visualization, we see the same rod rotating around its endpoint. This is a different rotation, and we would need to recalculate the moment of inertia. Now, we could do this by recalculating the integral. It's not particularly hard to do. But if we wanted to save time, we could use the parallel axis theorem. The parallel axis theorem provides a handy way of calculating the moment of inertia if the center of rotation is not located at the center of mass. All you have to do is multiply the mass of the object by the distance from the center of mass to the new center of rotation and add it to the original moment of inertia. In this case, the mass of the object was 9 kilograms. Since it is rotating about its endpoint, the distance from the center of mass to the new center of rotation is 1.5 meters. So following this calculation and this formula, we find that the new moment of inertia is the original one, 6.75 kilogram meters squared, plus the contribution added by moving the center of rotation away from the center of mass. That's 9 times 1.5 squared. The overall moment of inertia is 27 kilogram meters squared. Sometimes we run into more complex shapes. These can frequently be broken into simpler ones, and each of their moments of inertia added. For instance, this windmill has 3 blades, but we can treat each blade as being identical to a rod rotated about one of its ends, just like we examined in the last puzzle. So all we have to do is take the moment of inertia of a single rod, that's 27 kilogram meters squared, and multiply it by 3 to get the moment of inertia of 3 rods all rotating at their endpoints. That works out to 81 kilogram meters squared. It's possible to use techniques of direct integration to work out the moments of inertia for many other shapes, but to save time, we could more easily use a table like this. Each shape has its own moment of inertia, and it's easy to calculate based on its mass and other geometric factors. This table is reproduced in your textbook. For instance, if you have a solid sphere of mass 2 kilograms and radius 0.5 meters, you could just plug that information into the equation for moment of inertia of a solid sphere, 2mr squared over 5. Solving, this would give us 0.2 kilogram meters squared. In this video, we introduced the notion of moment of inertia, a measure of the difficulty of spinning an object. While we have discussed the calculation, we haven't yet explored its significance. That will be shown in the following videos.